Well, I would like to thank the organizer for the invitation. I will talk about the mean curvature flow and what happened at the first singular time. So this is the outline of my talk. So let's start with the mean curvature flow. We have a compact n-dimensional hypersurface in n+1 called M. And so let F0 is a smooth immersion of M into n+1. And we consider a one parameter family of immersion called Ft. So for Ft, we have the manifold Mt. And so, so we move Mt by the mean curvature flow. So this is the mean curvature flow. Here H is the mean curvature and nu is the unit normal of the manifold Mt at the time t. So let me recall that this is the mean curvature flow and it has a natural parabolic scaling. So we dilate the time by this factor and we dilate the space by the factor Q. So one of the nice property of the mean curvature flow is that it's the heat equation for this immersion. So it satisfies the maximum principle. So if we start with the compact manifold, and so if we bound the compact manifold inside a big sphere, then because the big sphere will shrink infinite time. So our manifold will shrink infinite time. But maybe there's some singularity before the shrinking. Okay? So in general, our mean curvature flow will develop singularity infinite time. And what is the characterization of the singularities? So the first one we can think of is the one given by Huisken, that we have the blow up of the second fundamental form of the manifold Mt. So this is the classical result. So suppose that capital T is the finite time singularity for the compact mean curvature flow. So as time the little t approaches capital T, we have the second fundamental form of the manifold Mt blows up. And we can ask, what other quantity can we think of? So we can think of all the scale invariant quantity. So suppose that we have the finite time singularity at the time capital T, and we let P and Q are positive numbers satisfy this relation. So, and then if we take the LPQ norm of the second fundamental form of the flow up to the time little t, so this is the definition of the LPQ norm, then actually this quantity will blow up at the little t approaching capital T. And in particular, in this relation, we can take P and Q equal n+2. So if we take P and Q equal n+2, then we have the quantity, and actually the quantity will blow up when we approach the first singular time. So let me mention that there are a couple of proofs of the above result. The first one, we can use the blow-up argument plus the compactness properties of the mean curvature flow. And the second proof is that we can use the blow-up argument and the Moser iteration. And one remark is that there is exponent n+2 in these quantities is optimal. So if we take the shrinking sphere under the mean curvature flow, then if we have this exponent to be smaller n+2, then actually we do not have the blow-up. So this in terms of the exponent, this is the optimal one. So now let me introduce the main result. So I think we mentioned that we could not improve the exponent, but however, the function with that same exponent, we can improve a little bit. So we give a logarithmic improvement of the second theorem. So in our approach, that actually we can show that a family of subcritical quantities concerning the second fundamental form will blow up at the first singular time. And the proof covers a very large class of such quantities, so but for simplicity, I will concentrate on the quantity. So now we concentrate the quantity we had before, which is scale invariant. Now I have a logarithmic improvement. So the theorem following. Suppose that if at the time capital T, I can control the quantity, which is finite, then actually I can extend my flow past the time T. So in other words, it means that suppose that the capital T is the first finite singular time for the mean curvature flow, then the quantity on the left-hand side will blow up. So this is actually a log improvement of the user result. Okay?
Can you keep adding logs to it? Just curious. You can put log square?
No, that's not true. Okay, so let me mention that there's also other result in other contexts. So actually, my result is inspired by the recent log improvement of the protein criteria for the Navier-Stokes equation. So what's the criterion? So the classical protein criterion said that if you have a weak solution U of the Navier-Stokes equation in 3 dimensions, then if this weak solution satisfies that U to the cube to the fifth integral is in space and time, then actually you have global regularity for the weak solution. And later, Shen and Vassar, they improve a little bit the classical protein criterion by saying that if the weak solution U satisfies that U to the fifth divided by log of 1 plus U is integral in space and time, then they have the global regularity. And the proof in Chan Vassar's paper is by the Stokes technique. So the question we can also ask is, can be other results in some other setting like the heat flow of harmonic map or the rigid flow? We don't know. But many of the steps in the proof, I think will be carried over to the rigid flow and the harmonic map. So let me give you the idea of the proof. So this is the key point in the proof. First of all, because our quantity is subcritical, we could not use the blow-up argument because the blow-up argument will not give us anything. So the blow-up argument also only give us some information when we have the critical quantity or supercritical quantity. But in this case, because we have the subcritical quantity, so we could not control anything by using the blow-up argument. So we have to use some other method. But the key point is that for any time positive time, so the second fundamental form at the time t, or the manifold mt, can be bounded in an affine way by the second fundamental form to the power n plus 3 in space and time. So this is the key point. So the precise statement is the following. So if I take any lambda from the interval from 0 to 1, and then I can find a constant C lambda. And the important thing is that the constant C lambda just depends on lambda and the space dimension n. It doesn't depend on any other structure or any initial data. So then, if I take any lambda, so if I take any time capital T which is greater than lambda, then I can bound the maximum of the second fundamental form of the manifold MT by this quantity. So then our result will just follow from the Grunwald-Tau argument for the maximum of the second fundamental form. So because I have some time, so I will just get very briefly how to get the theorem from this inequality. So let me take any time called tau 1, which is smaller than the time capital T. Then by our proposition that for any time little t greater than tau 1, you can bound the second fundamental form at the time little t by the quantity on the right hand side. And then for notational ease, we just let this quantity to be ft. And I introduce the function psi, which is s logs of 2 plus s. That's show up in our inequality. So I define the function gs, which is the integral on the manifold ms of the quantity. And by our assumption, if I integrate from the time 0 to capital T of the function gs, it's infinite. So I will rewrite my inequality here, this inequality in terms of the function f. So in terms of function f, I can bound by this inequality. Now I split my quantity because I have a to the n plus 3. So I split up that term into the function psi and this term. And now I bound the second fundamental form by the maximum of the second fundamental form. And then this is just the function f, and this is my function g. So I let the quantity on the right hand side, I call it the function ht, then my inequality becomes this inequality. So now I rewrite my inequality as following. So by the definition, the derivative of my function h is just this function, and because my function psi is increasing, so I substitute the function f by something bigger equal to function h. So from that, I can use the Grunwald inequality to conclude that if I define my function psi tilde y is the integral from c to y of 1 over psi s ds. Okay. Then, actually, I can bound the maximal of my function psi tilde up to the time capital T of the function ht, because the quantity on the right-hand side is finite by our assumption. Okay. So what happened for the function psi? So remember, this is the key computation. So if you take the integral from 1 over psi s ds of the function psi to from some fixed number to infinity, then you have the blow up. So, but in inequality here, this is finite, so it means that the function ht must be all the way bounded up to the time capital T. But because the function h controls the function f, and the function f is just the maximum of the second fundamental form, so it means that I can bound my second fundamental form up to the time capital T. So, because I can bound my second fundamental form up to the time capital T, it means that I can extend my flow by the time T. So now I will explain how to prove the key result. So to prove the key result, we have a scale version, and the scale version is the following. So that if you bound the second fundamental form to the power n plus 3 up to the time 0 to 1 by a small constant C0, and C0 just depends on dimension n, it doesn't depend on any other information, then I can bound the second fundamental form from the time 1/2 to the time 1. Okay, why that is true? So if we look at the evolution of the second fundamental form square, and this is the evolution, we see that the second fundamental form square satisfies this inequality. So we see that it satisfies a parabolic equation, so d of dt a square smaller than Laplace a square plus f of a square, and because my function f is 2 of pi of the a square, and because I have the bound of s to the power n plus 3, so it means that my function f is bounded in space and time of the exponent n plus 3 over 2. But because remember that we are ambient space is n plus 1 dimension, but our manifold is just m dimension. So if we look at the parabolic equation, we count time at 2 dimension and the space n dimension. So in this equation, if we look at the use of Moser iteration, the critical exponent is n plus 2 over 2. But because here we can bound something in bigger power, so it means that we have a bound on the supercritical quantity, so it means that it should follow that we can bound the second fundamental form. However, there's one twist, so this is the key, the idea. We can bound the infinity norm of our second fundamental form in a smaller set by the beta norm of the second fundamental form in some bigger set. And the proof will use Moser iteration and a modified Michael-Simon inequality. So because we have to use Moser iteration, so we have to use overlap inequality, and the overlap inequality, remember that in our equation, because we have the change in matrix and change in the Laplacian, so we have to use the modified Michael-Simon inequality is the replacement of the overlap inequality. So what is the original Michael-Simon inequality? So if I have the manifold M have a surface in n plus 1 dimension, if I have a function f which is a negative, then I can bound the L n over n minus 1 norm of f in terms of the quantity on the right-hand side. And because if this inequality is not enough for our purpose, so the right inequality is the following. So if M have a surface in n plus 1 dimension, then for any function v which is Lipschitz on the manifold M, I can bound the L 2n over n minus 2 norm of v in terms of the quantity on the right-hand side. So this is one of the main inequality we use. And the proof is very simple. We use the original Michael-Simon inequality and the interpolation inequality. However, there's one catch over here. If in this quantity you see that you have the Ln plus 3 norm of the function of the mean curvature, and so we know that if we bound the second fundamental form up to the power n plus 3, then we can bound this mean curvature up to the power n plus 3. However, if we look at, if we do the yield the Michael-Simon inequality and yield the interpolation inequality, and if this power 2/3 here, if it's something else, it might be something like, say, 5 over 2 or something like that, then our approach completely fails. So it's very important that in this inequality, 2 over t is smaller than 1. So that's the crucial idea, crucial one in the proof. So Okay, that's just how we approach the problem, how we carry out the micro Simon and Moses iteration, and that's it. Thank you very much for your attention.
Questions or comments? So now the first type singularity fail-state one, fail-state, obviously, fail-state condition for intervals.
Yeah, so if you can take any integral that is 1 over psi, and you define any function psi which is infinite, then you can modify the proof and you work that. Okay, that's good. So your question, your previous question, you asked what is you replace by log, but by log square, and actually if you plug in that integral is finite. So it's not true. So it means that we could not improve more. Improve by log, but could not by log square.